Hi everyone, Dr. P here, and in this lecture video we'll be starting in on chapter 20, which is carboxylic acids and nitriles. And this first lecture will look at carboxylic acids, just a general overview, and then also some properties of carboxylic acids. So carboxylic acids look like the following. They have what looks like a carbonyl, a C double bond O, but also an alcohol, an OH. And that gives them their name, carboxylic. So the carbonyl and the hydroxyl form a carboxyl group. So they are carboxylic acids. Now we can make some derivatives of these. And the text does mention a few. These include acid chloride, where instead of the OH we have a chlorine. We could also have an acid anhydride, which is really two carboxylic acids joined together with loss of water, hence the term anhydride, without water. We can also have, instead of an OH, we'll have an OR there. We'll have an alcohol, what came from an alcohol, and that's called an ester. And then the last one that I'm really going to focus on is amide. Now we could have R groups, alkyl groups instead of hydrogens here, but this is the sort of core structure of an amide. All right. Now we'll talk about all of these later on, actually in chapter 21. But for now, let's focus on carboxylic acids. And one of the most important properties of carboxylic acids, of course, is that they are acidic. For example, we could draw the following dissociation reaction. Where our carboxylic acid is splitting up into the carboxylate ion plus a proton. And we, of course, could have an acid dissociation constant for this, which is given by COO minus, given by the following equation here, RCOOH. And then, of course, our pKa is minus log of Ka. Now, there are some typical pKa values in tables 20.3 and 20.4 in the text. But I'll just give a couple of examples here. So let me draw some acid structures and then give their pKa's. So something like acetic acid has a pKa of 4.76, but trifluoroacetic acid with 3 fluorines attached to the carbon, the alpha carbon, has a pKa of 0.23, which is a borderline strong acid. Now, why is that? Well, our acidity is affected by structure. So anything that can stabilize the negative charge on our conjugate base will give a stronger acid. In particular, we're going to look at inductive effects. So let's just say here, anything that can stabilize negative charge on conjugate base by induction will give a stronger acid. Because remember, the more stable the conjugate base, the stronger the acid that it came from was. So think back to 12A, and you may want to review some of the lectures. But let's remember REO. So we used this little mnemonic here to remember the different structural factors that affect acid strength. We have A, atom identity. Well, in our conjugate base, since their carboxylic acids all have this carboxylate group as in their conjugate base, our negative charge is always on oxygen. So we don't have to worry about that. R, resonance, well, they all have the same resonance structure. We'll look at that in a little bit later. Induction, well, that's what we're really interested in here, is inductive effects. And then orbital identity we're not going to worry about because negative charge is in a sp3 orbital. So really what we're interested in here is the inductive effects. So anything electron withdrawing, so electronegative stuff, will pull electron density towards itself and away from the negative charge on our carboxylate. So if I just have hydrogens on my R group here, it won't stabilize too much, but if I have some halogens like fluorine, chlorine, then that will have a electron withdrawing effect to help stabilize that negative charge. And I should note that the effect does depend on how far away the electron withdrawing group is. So if I have a beta chloro or 3-chloro butanoic acid, my pKa is around 4. But if I have the 2-chloro butanoic acid, my pKa is a bunch lower, 2.86. So the further away the electron withdrawing group, the less the effect. All right, well, let's take a closer look at the carboxyl group now. All right, so if I look at my carboxylate ion here, I can draw a resonance structure, of course. And why don't I go ahead and just push some electrons here to show you. Boom. And, oh, forgot to put my lone pairs on that guy. There we go. And So now I've got O, negative charge, and double bond O. And if we were going to write this out as sort of an average of these structures, it would look something like this. And so in reality, the negative charge is delocalized over both oxygens. So once we pull that proton off, we get this carboxylate. And, you know, let's say we had some kind of sodium carboxylate salt here. Sodium would be complexed with this right here. Now, if we look at some physical properties, we'll see that carboxylic acids have typical solubility for polar compounds. But carboxylate, carboxylate salts, I should say, are more soluble in water. Again, when I refer to solubility, I'm usually talking about water. So if I had my carboxylic acid here, this is soluble. Let's say water soluble if R has less than or equal to 3 carbons. So if you've got 4 carbons or fewer for our carboxylic acid, that's going to be water soluble. Now I could react this with NaOH, do an acid-base reaction, and I will get R, C, double bond O, O minus, Na plus H2O, and this is my carboxylate salt. And this will be water soluble with longer R groups. Okay. Another interesting thing is, and some of you who might have carboxylic acids as unknowns in the unknowns lab, you know that sort of medium length carboxylic acids are pretty darn smelly. But if you were to neutralize with a base, you would get a carboxylate salt, which in addition to being water soluble is also not that smelly. So that's something to think about. All right. The last thing I wanted to talk about was benzoic acids, and let's look at some substituted benzoic acids. And this is really table 20.4, I think, in the text. So we'll look at our acid here. If we had our parahydroxy benzoic acid, our pKa here is 4.48. Now, if we just had plain benzoic acid, our pKa is 4.19. So what's going on here? Well, let's take a look at some other substituents. If we had parachlorobenzoic acid, our pKa is 4.0. And then paranitrobenzoic acid, our pKa is even lower, 3.41. So over here we have a stronger activating group. And these will give higher pKa's. That is, they make things less acidic. Whereas over here, if we have stronger deactivating groups, we'll get stronger acids and lower pKa's. Now, why is this? Well, let's think about it. If we pull off our proton and get a negative charge, our carboxylate salt, how stable is this going to be? Well, I've got a negative charge, but over here I've got something that's electron donating. It's got those lone pairs. So that's not really going to stabilize that negative charge. It may destabilize it slightly. But if I have something that's electron withdrawing, like a halogen, or especially something like NO2, where remember we have that positive charge on nitrogen, that's really going to help pull electron density away from my carboxylate anion here and help stabilize that. So again, it's an inductive effect and sort of takes place via the aromatic ring there. But it is noticeable. And one interesting thing, the text mentions this, I'm not going to write it down, but just sort of mention it. You can actually use this to figure out if a given substituent is activating or deactivating. So it's relatively easy to determine a pKa. You guys did that in Chem 1B, unless you took it online, but you did that in Chem 1B. And it's harder, though, to measure rates of electrophilic aromatic substitution reactions. So what you could do is say, have your substituted benzoic acid and see, like, let's say you had sulfonyl. You have the sulfonyl group there instead of the NO2. You could measure the pKa of that, and based on the relative pKa compared to these guys, you could figure out where it is sort of in the line of reactivity. And it should be in between I believe the NO2 and the Cl. And so the intermediate, the pKa tells you something about how deactivating the group may be. A stronger deactivating group gives you a lower pKa in your benzoic acid. All right, so that is about it for this video, and next time we'll go ahead and take a look at ways of preparing carboxylic acids as well as reactions of carboxylic acids. So until then, stay safe out there. Bye now.